Good morning and Assalamualaikum. In assignment part B, we are required to find and modify an application problem that can be formulated as a linear programming LP problem with at least 3 decision variables and 3 constraints. In this part B question 1, our group choose to change TOEICO problem to our LP problem, which is Sweet Tooth Company. In TOEICO problem, there are 3 types of toys, which is train, trucks, and cars. However, my group changed into 3 types of candy, which is lollipop, bubblegum, and jelly beans. All the numbers we does not change. However, the variables we change, which is the x1 will be a lollipop, x2 will be the bubblegum, and the x3 will be the jelly beans. These are the constraints, which is operation A, operation B, and operation C. And the decision variable is x1, the number of lollipop produced daily, x2, the number of bubblegum produced daily, and x3, the number of jelly beans produced daily. After we have the LP problem, we solve the LP by using a window. Here is our application window, and here we key in all the data that we have. Here, as you can see from the window, this is the data that we have keyed in from the Sweet Tooth Company LP problem. After we key in the data, we click Reports and click Formulation. After that, we click Solve. You will see the data. From the first part, you can see it is the maximization problem, which is 3x1 plus 2x2 plus 5x3, and subject to, which is of operation A, operation B, and operation C. This is the objective function value, which is a value of z which is equal to 1350. And the x2 and x3 here is the basic variable, whereas the x1 is a non-basic variable. The reduced cost for basic variable is always 0, while x1 is non-basic variable, therefore the reduced cost is 4. By mean, increase of x1 will decrease z by 4 ringgit. We can say that x1 is unprofitable variable. Here is the slack variable. S1, S2, and S3 are the slack variable for constraint of operation A, B, and C. The value of S1 and S2 is 0, while S3 is 20, since S3 is a basic variable. And there is no dual price for S3. By definition, the corresponding dual price for operation A is 1 ringgit, for operation B is 2 ringgit, and operation C is 0 ringgit. A unit change in operation A capacity is RM1. Unit change in operation B capacity change Z to 2 ringgit, and unit change in operation C capacity change Z to 0 ringgit. Here is the optimality range for lollipop, bubblegum, and jelly bean. X1 is a lollipop, X2 is bubblegum, X3 is jelly bean. Here we see from a lollipop, which is the current coefficient is 3, and the optimality range is from -infinity to 4. And we see from a bubblegum, which is the of coefficient 2, the range is from -2 to 8. And the last one is jelly beans, which is the current coefficient of 5. Similarity range is from to negative 2.67 until infinity. And the last one is right hand side ranges, which is the feasibility range, which is 0 of operation A is 430, and the feasibility range is from negative 200 until 10. For operation B is 460, and the feasibility range is from negative 20 to 400. And last one is operation C is 420, which is the range is from negative 20 until infinity. That is how we read LP problem from Lindo. Let us proceed to next questions.
Next, it's time to discuss the sensitivity analysis in details from the problem that has been solved in Lindo. First, we look at the problem when there are changes on the right-hand side and all conditions are feasible. For example, suppose that the manufacturing time available for operation A, B, and C of the sweet tooth model are changed to 390, 442, and 450 minutes respectively, meaning that the right-hand side of the constraint in the original LP model are changed to a new value. Here we can see that the right-hand side of the first constraint is changed from 430 to 390, and the second right-hand side is changed from 460 to 442, and the right-hand side of the third constraint is changed from 420 to 450. Therefore, the changes or the differences of the right-hand side can be calculated by new value of right-hand side minus the original value of the right-hand side. So, we get D1 equal to negative 40, D2 equal to negative 18, and D3 equal to 30. And then, obtain from the right-hand side ranges in Lindo solver, we can determine the feasibility ranges. For D1, the minimum range or the allowable decrease is up to 200, and the maximum range or the allowable increase is up to 10. While for D2, the minimum range or allowable decrease is up to 20, and the maximum range or the allowable increase is up to 400, while the minimum range or allowable decrease of D3 is up to 20, and the maximum range or allowable increase is infinity. And since all D1, D2, and D3 are within allowable increase and allowable decrease, therefore all conditions are feasible. This also means that the dual prices will remain applicable to calculate the new total profit or the Z value, which can be computed from the dual prices as new Z value equal to original Z value plus dual prices times its differences respectively. Dual prices here is 1, 2, and 0, which can be obtained from the Lindo solver. We substitute and calculate the value, and we get new Z as 1,274 ringgit. This means the changes of the right-hand side of the three constraints has reduced the total profit by 76 ringgit. Next situation is at least one of the condition is infeasible. Suppose that the manufacturing time available for operation A, B, and C of the sweet tooth model are changed to 460, 440, and 380 minutes respectively, meaning that the right-hand side of the first constraint is changed from 430 to 460, the right-hand side of the second constraint is changed from 460 to 440, and the right-hand side of the third constraint is changed from 420 to 380. And we determine the differences, which we get D1 equal to 30, D2 equal to negative 20, and D3 equal to negative 40. The same as the previous situation, the feasibility ranges can be obtained from the Lindo. As we can see here, D2, which is equal to negative 20, is within the feasibility range. But D1, which is equal to 30, exceeded the maximum allowable increase, and D3, which is negative 40, exceed the maximum allowable decrease. Hence, the current solution doesn't remain feasible, and further calculation are needed to find the new optimal solution by using the dual simplex method. To do the dual simplex method, we have to update the optimal value by replacing the right-hand side value of Z, X2, X3, and S3 with new value. Same as before, Z value and BV's value can be obtained by adding original value with dual prices times D1, D2, and D3 respectively. And from the computation, we get the updated Z value equal to 1340, X2 equal to 120, X3 equal to 220, and S3 equal to negative 100. Then we substitute the value inside the updated table. As usual, we have to find the leaving variable and also the entering variable, and then we proceed with ERO until we find the optimal table. Here, table 1 is the optimal table because there is non-negative coefficient in row 0. Also, there is no negative right-hand side. Then, we obtain the new optimal solution as stated below, which is X2 equal to 95, X3 equal to 220, S2 equal to 50. Meanwhile, X1, S2, and S3 are equal to 0. While the new total profit, Z, equal to 1290.
Assalamualaikum and a good day everyone. So I'm going to continue with the second problem in question 3 part B, which is when there are changes in the objective function coefficients. So we're going to take a look at the first condition when all conditions are satisfied. So from the LP problem that we have created, so we suppose that the objective function in sweet tooth problem is changed from Z equals to 3s1 plus 2s2 plus 5s3 to Z equals to 2s1 plus s2 plus 6s3. As you can see here, the revenue is changed for each type of candy. So first we're going to let the D1, D2 and D3 to represent the change in unit revenues for lollipop, bubblegum and jelly beans respectively. And we're going to find the different change for D1, D2 and D3 by subtract from the revenue of new objective function to the original revenue of the objective function. As we can see here, D1 we get negative 1, D2 we get negative 1 and D3 we get 1. So we are going to take a look and compare into the optimality range obtained from Lindo solver. As we refer back to the solver Lindo that we have done, this is the optimality range, which is the allowable increases and the allowable decreases. So when we refer the optimality range, the value of D1 negative 1 is within the optimality range, which is within the allowable increase and allowable decreases, which is between negative infinity to 4, and D2 also within the optimality range, negative 1, which is in between of negative 2 and 8, and D3 also within the optimality range, which is 1 between negative 2.67 until positive infinity. So since D1, D2 and D3 value are all within the optimality range, which is within the allowable increases and allowable decreases, therefore we can conclude that all conditions are satisfied and the optimality will remain unchanged. So we can get the new total profit or the new Z value by substitute back the value of D1, D2 and D3 and also the value of S1, S2 and S3 into this kind of function, which is the new objective function, and we will get the new total profit, which is 1480 ringgit, which this shows that the proposed change will keep the current solution optimal but with a new value of Z. So next we move to the second condition, which is at least one of the condition is unsatisfied. So we suppose that the objective function in sweet tooth problem is changed from maximize Z 3s1 plus 2s2 plus 5s3 to maximize Z 3s1 plus 6s2 plus s3. So same as the condition above, so we will let D1, D2 and D3 represent the change in unit revenues for lollipop, bubblegums and jelly bean respectively. And we will find the value of D1, D2 and D3 by subtract the revenue value from the new objective function and the original objective function. So we will get D1 is 0, D2 is 4 and D3 is negative 4. And as the same situation as the condition above, so we will compare with the optimality range obtained from Lindo, as we see, the value of D1, D2 are within the optimality range, which is within the allowable increases and allowable decreases. However, D3 exceeded the allowable decreases, which is supposedly allowable decreases is negative 2.67, but unfortunately the value of D3 is negative 4. Hence, one of the conditions is unsatisfied. Therefore, the optimality of the current solution is changed, and further calculations are needed to find the new optimal solution by using dual simplex method. So in order to find the new optimal solution by using dual simplex method, so we have to find the new value of z, which is we have to substitute the value of s1, s2 and s3 into the new objective function, and we will get the new total profit, which is 830. And we have to do also the simultaneously optimality condition, as we have s1, s1 and s2 with its coefficient, as s1 is negative 3, S1 is 3 and S2 is negative 1. As we refer back to this optimality condition, we will see that the only S1 is satisfied while S1 and S2 is unsatisfied. Therefore, the current solution is no longer optimal. So we have the coefficient for S1, S1, S2 and also the new total profit of Z. We will have to update our table and we will transfer and substitute the value of S1, S1 and S2 and also the right hand side for the row 0. And as usual, we have to pick the entering variable, which is negative 3 is the most negative coefficient, so S1 is the entering variable, while LV, which is the leaving variable, is S3 as the ratio is 10, which is the smallest ratio. And we will undergo ERO, and this is the updated, which is the table 1 after the RO process. So we'll see that this is the optimal table because there is non-negative coefficient in row 0 and there is no negative right hand side. Thus, table 1 is the new suboptimal table with a new optimal solution as stated below. S1 is 10, S2 is 102.5 and S3 is 215. So from here, we will get the new total profit, which is the new value of Z, which is 860 ringgit.